Hello everyone, I'm RQ. I make these interactive light sculptures which I call Lumanoi. Since the last video, you've all made it very clear that the next thing you want to hear about is the electronics in my light sculptures. So in this video, I'm going to go over the overall electronics design, the reasons why some things were designed the way they were, and provide some hints about how it might be evolving in the future. This is the high-level block diagram of the electronics in a Lumanoi interactive light sculpture. We have a main control board, which connects to a series of cell boards via a ribbon cable. The main control board also connects to two ambient light sensor boards and a touch control board, and we're going to go over those a little bit later in the video. The bus that connects the cells is not really a bus in the truest sense, but rather a port-to-port daisy chain. The cell boards are enumerated automatically at startup, with cell 0 being the cell that's closest to the main control board. There are 20 conductors in a ribbon cable, which I'm sure seems like a lot, so let's take a closer look. Here is the cable pinout. Half of the pins are ground pins, 4 of the pins are for 24-volt power, and the rest are digital signals. You might be noticing that the first 2 pins look flipped. With the exception of the first 2 pins, all odd pins are ground. Indeed, in the first version of this pinout, all of the odd pins were ground, and that would have been fine had it not been for me trying to connect a ribbon cable to the bare cell boards on occasion. The problem with this is that the keying for the ribbon cables, the part that prevents you from connecting the ribbon cable backward, it isn't present in the bare uninstalled circuit board. Occasionally, I would either misalign the pins or flip the connector around entirely. Whenever that would happen, the results were catastrophic, sometimes frying every single cell board in the daisy chain. Flipping those first 2 pins around now creates a dead short whenever the connector is inserted in the most common incorrect orientations, and this has saved my butt many times. This is what the most recent cell board design looks like. I know it looks like there's a lot going on here, so let's break it down. On it, we have 8 smart LED chips, 4 infrared LEDs, 1 dual op-amp, 1 photodiode with an infrared mask, 1 photodiode without an infrared mask, a 20 MHz oscillator, an ATmega 1608 microcontroller, and a 5-volt DC-DC buck converter. The smart LED chips are HD108s, which have 16 bits per channel with an additional 5 bits per channel of current control. With some fancy software tricks, I can get an effective 20 bits of linear control per channel, which is way more than the 8 you could get with a NeoPixel. This gives me the dynamic range to have my light sculptures look fantastic, even in extremely low light conditions, without posterizing like you would see with an 8-bit per channel chip. The dual op-amp is for 2 transimpedance amplifiers for the photodiodes. When I started working on this project, I didn't even know what a transimpedance amplifier was. If you're curious, look it up. It's handy. I've stopped populating the photodiode without the infrared mask to reduce the production costs in recent runs, and I'll likely eventually switch to a single op-amp rather than the dual op-amp. Or maybe I'll switch to a microcontroller with the built-in op-amp. We'll see. The ATmega 1608 microcontroller is where the magic lives for the hand proximity detection. The actual algorithm used for hand detection is a bit complicated and deserves its own video. But in the meantime, I'll give you a quick hint. If you take out the infrared cut filter on a camera with a rolling shutter, like I did with this old webcam, and point it at one of my light sculptures in the dark, this is what it looks like. It's pretty trippy, no? On the back of the cell board, we have 2 connectors for the IDC ribbon cables, one for upstream and one for downstream, an identification LED and a debug port. These boards fit into a 3D printed part I call the backplate, which is parametrically generated from Voronoi point data. Due to the automatic rotation of the cell board mount to better support the wiring order, no 2 are exactly alike. They also have the keying for the IDC connectors to ensure that they are not inserted incorrectly. This saves a little bit of money that I would have otherwise had to spend on a shrouded connector. The back plates are printed with Bamboo Lab white PETG HF filament, which is the most opaque white PETG filament I have found so far. This is the current iteration of the Lumanoi main control board. The brain is an ESP32S3 Room 2 module. For I/O, there is a 20-pin Lumanoi cell board connector, 2 independent I2C buses, and 1 extra expansion port with 3 I/O pins plus power. There is a buck converter to step down the 24 volts to 5 volts. The 5 volts is stepped down to 3.3 volts with a linear regulator. The smart power switch IC has lots of features like the ability to monitor the current and the die temperature. It also has automatic overcurrent protection. The switch allows me to cut the 24-volt power to all of the cells, as well as monitor how much power they are using when they are running. The dip switch has 3 toggles: microphone disable, radio disable, and factory reset. By default, everything is enabled, but the microphone is currently unused in the firmware. A factory reset is triggered by flipping the switch and rebooting. It remembers the position of the switch and will perform a factory reset if it reads differently than it was at the time of the last factory reset. There are 2 push buttons, one for reset and another button for funk. This board fits into a 3D printed enclosure which slides into a cutout in the outer frame and locks into place with 2 screws. While the firmware for the much earlier prototypes used MicroPython, the current firmware is written entirely in Rust. I have a dream one day of integrating MicroPython into the current firmware so that people can add their own features using MicroPython, but alas, that is at least a year down the road. I wanted my light sculptures to have some way to control them directly, either to adjust the brightness or to change the mode. I could have added physical buttons, but I didn't want to add any moving parts that could wear out, so using capacitive controls seemed like a natural fit. There are a lot of boards for doing this sort of thing, but nothing quite worked the way that I wanted, so I ended up rolling my own solution again. These boards have 2 capacitive touch buttons on either side of a wide touch slider. It connects to the main board via I2C. I machine out these indentations in the frame at fabrication, and the boards get affixed behind the indentations with double-sided tape. The result is a set of solid-state controls that melts seamlessly into the wooden frame. The microcontroller on this board is an ATtiny 1614, and I wrote the firmware for that too. By the way, I'm thinking about selling these, so let me know if you'd be interested in buying something like this to use in your own projects. My light sculptures sense the ambient light level in the room and automatically adjust the brightness of the light sculpture to match. There are 2 ambient light sensors, so that if one is in the shadow, the other is hopefully not. The ambient light level algorithm was designed to brighten quickly, but darken a bit more slowly to match the actual physiological response of our eyes to rapidly changing light levels. Originally, I was using these ambient light sensor modules from Adafruit, and they worked pretty well. However, I wanted to have the light sculptures adjust not only to the brightness, but also the white point based on the correlated color temperature of the ambient light in the room. And the VEML 7700 chip that was on the Adafruit boards just wasn't up to the task. I wanted to use the VEML 3328 chip, but I couldn't find anyone who made a breakout board for that chip. So I made my own. It is a dead simple breakout board that is mostly a drop-in replacement for the Adafruit model, except that it can also be used to calculate the correlated color temperature. It isn't a 5-volt tolerant part like the Adafruit board, but who cares? Incidentally, I sell these ambient light sensor boards on my website, so check out the link in the description if you'd like to use this board in your own projects. The result of all this attention to detail is that, hopefully, you never notice. My light sculptures should just look great, no matter how dark or how cool or how warm your ambient light is. While it's certainly not perfect, I feel pretty good about all the hardware that I've developed for this project. And this wasn't even all of it. I didn't cover the latest test jig or all the previous wacky hardware iterations. While the cell board and the main control board are not for sale on their own, I am working on some hand detection only boards that daisy chain together and use the same hand detection algorithms. I'm developing them largely to support making architectural scale interactive light sculptures, but I think I might sell them individually too. Let me know in the comments if that's something you would be interested in. Remember, if you want to help this channel grow, the best thing you can do is like, subscribe, and comment. Thank you for watching. Look, Ma, I made a voltage divider.